So we're going to have a small rappel on what we did last time on the atom itself. So like we said atomistic is basically the study of the atom. Now we're supposed to understand what the atom is and how the development or the discovery of the atom came about. So it starts from way back with the study of the 4 elements of nature, that is fire, water, the earth, and air. And this was done by, I would say, a famous philosopher by the name of Aristotle. So that was his first insight over what the atom would actually be like. So we're giving a small rappel, then we're going to go into detail with what we are supposed to do today. Then later on, we look at John Dalton coming up with a definition to say, okay, an atom should be something that cannot be divided any further, which means it should be a unit of matter. Now, you should reach a point where you cannot divide it any further. That was his definition to say, okay, no, an atom should be a unit of matter that cannot be divided any further. Now, matter in this case, like we know, matter has 3 states. It can be a liquid, it can be a gas, it can be a solid, depending on what you are actually studying. So in our case, or in his case, he might have used, say, a lemon, he might have used a coin. Then in our case, last week, we used the currency, the Zambian currency. We were saying, in Zambia, the lowest currency you would have possible, like the lowest currency, the lowest note, in other words, is the 50 ngwe. There is no currency, like there is no note after 0.5 ngwe, there's nothing. So in our case, if we were John Dalton, we would say 0.5 ngwe is the atom of the Zambian currency because it cannot be divided any further. That was his definition. Then he added on something that we are calling the law of proportion. Then for those that are doing CHIMIE reactivity, there's an aspect called the law mass action. So the law mass action and John Dalton's second law of proportion states that given a unit mass of a substance, because you know that you've got matter, and matter is anything that anything that occupies space and has mass. Given a unit mass of any substance, it can be a liquid, a solid, or a gas of, for example, carbon dioxide is reacted with hydrogen to form methane and carbon monoxide. That is called steam reformation. Or we can have carbon reacting with oxygen to give carbon dioxide. Now, assuming that we start with 1 gram of carbon and we have 2 grams of oxygen. Now, the law of proportion states that if you're starting with 1 gram of carbon and 2 grams of oxygen, definitely you are going to end up with 3 grams of carbon dioxide. Now, we know that carbon dioxide can have 2 states, or assuming that it can have 3 states. Carbon dioxide can exist in its liquid state. Of course, that is going to be dry ice when the ice is in its liquid state, or it might be solid. We are calling that dry ice, or it might be a gas. Carbon dioxide exists as a gas. So it can be in the 3 states of matter, liquid, solid, gas. Now, the law states, if you start with 1 gram of carbon and you react 1 gram of carbon with 2 grams of oxygen, definitely you're going to have 3 grams of carbon dioxide formed at the end of the day. Now, that is the law of proportion. You start with 1 gram, you have 2 grams there, and the unit mass is 3 grams. The law of conservation of energy is being applied there because there is nothing that is being lost to the system. Of course, if the reaction is exothermic, the only thing that's happening is that the heat is being produced in the environment, but there is conservation of the matter that you have in the system. There is conservation of matter that is happening in the system. Now, for an aspect of thermodynamics, there is what you call a system that is isolated, where there is no interaction between the environment and what's happening inside. So we're assuming whatever we're going to be doing is going to be done in an isolated system, where there is going to be conservation of energy and there is going to be like conservation of the mass that we have started with. That was his second law of proportion. It says that, okay, start with 1 gram of carbon, 2 grams of oxygen, you get 3 grams, regardless of the state. Look, carbon can be carbon can be solid, oxygen can be a gas, At the end of the day, when you react the two, when you have 1 gram and 2 grams of oxygen, at the end of the day, you are definitely going to have 3 grams, because there is nothing that's going to be lost to the system. Of course, carbon dioxide being a gas can be lost, but the quantity, or let me say the mass of carbon dioxide, in as much as it is going to be lost to the environment, it's still going to maintain the 3 grams. That was his law of proportion. It is applied in reactions at equilibrium, and we are calling that the low mass action, which states that given 2 reactants, A plus B gives C and D. Now, the stoichiometric coefficients that are going to be used to balance up this reaction are going to be equated to what we are calling the equilibrium constant expression, which is equals to the product over the reactants, and each reactant or each product is going to be raised to the power of the coefficient that you have used to balance the chemical reaction. That is what you call the law of mass of action. It's just a derivative from John Dalton's law. Then looking down further, we have Ernest Rutherford and J.J. Thompson. So these guys came up with the famous discoveries of the electron and the noyau, the nucleus. Now, when you look at J.J. Thompson's discovery was based on the electron. So the electron being the only charge that is negative in the orbital of the atom. And on the other hand, Ernest Rutherford looked at the discovery of the proton. Now, when you look at the two, they are complementary discoveries. It's one of the cases where you study, let me say, you are studying microbiology. Now, you know that in microbiology, there's what you call gram-positive bacteria and gram-negative bacteria. Now, knowing that there is gram-negative, you can assume it's not correct, but you can assume, you're allowed to assume. You can assume if I have gram-negative, it means there must be gram-positive somewhere else. So it's the same principle. When J.J. Thompson found the electron, it was like, say, it was an open road for everyone who wants to actually look at the atom. So it was Ernest Rutherford that now came up with the discovery of the nucleus. He said, if there is an electron around the orbital, there must be a force inside the atom that is responsible for let's say balancing the charge. Because with further discoveries and the modern this definition of an atom, you guys have learned that an atom is electrically neutral because the number of protons equals the number of electrons, which is one of the justifications that Ernest Rutherford would have gone for, to say that, okay, if we have an electron that is moving around the nucleus, there must be an opposing charge that exists somewhere in the atom, and he found that that was the center, and it is responsible for the balancing of the charge. Now, you have J.J. Thompson and Ernest Rutherford coming up with the definition of the atom now in regards to what particles are found in the atom. J.J. Thompson talks about the electron, and Ernest Rutherford talks about the nucleus that contains the positive part. Now, as people gained understanding of what the atom is and what an atom basically defines, like what particles are found in an atom, all those things, the definition of mass and proportion, etc. Now, Albert Einstein, Niels Bohr, Planck, everyone came together, and now everyone was debating, because it was all about who's going to get credit at the end of the day. So you have Niels Bohr and Albert Einstein. So Albert Einstein was I would say his work was a prophecy for someone else in the future. Of course, his work when he was looking at the discovery of the elementary particles found in the atom, his work was not appreciated there and then, because it was kind of conflicting with what Niels Bohr's principles were actually stating. So his work there was not appreciated because it was conflicting with Niels Bohr's principles. And Niels Bohr came out as outstanding, and it really was something for for Sir Isaac, for Sir Albert Einstein. So Albert Einstein's work is going to be appreciated by a famous scientist who has done what you call the light and wave duality principle. So right now, Albert Einstein's work is like he's done nothing, but it's a prophecy for someone else who is in the future. Now, Albert Einstein's experiment was just what we call the photoelectric effect, where you have a metal and you have a special type of radiation. So this radiation can either be an alpha or a beta. Now, depending on what type of experiment you're dealing with, you are supposed to consider the penetration powers of these wave, what do you call it? The particles that are going to be used, the radiation. So assuming we're using an alpha particle and we want to knock down an electron from a given metal, we are saying an atom is anything that can occupy, or anything that is like, it's building up, it's a buildup that makes up matter. Now, the metal that you're using there is actually a buildup of small particles. So his experiment was based on, okay, you have this radiation, that is alpha, and you have this metal plate made up of atoms. What is going to happen if I heat up the radiation and try to see what's going to happen if the metal is going to be hit with this radiation that I'm using? If it's alpha, it's gamma. So most of the times the wavelength that is proposed is 1.5 Armstrong. So that is the proposed wavelength, but the energy might depend on what you are actually looking for. So his experiment had two conditions. If the energy of the radiation is greater than the energy that the metal possesses, it means you are going to have an electron that is going to be knocked out from the metal. Now, the electron that's going to be knocked out from the metal is what we are calling a photon. Now, a photon is a unit charge of energy. So the photon actually shows, or it defines to say, okay, in this atom, there is an aspect of what we call the particle nature. And in this atom, there is an aspect we are calling the wave nature, which we are going to call in future the wave and particle duality principle. Now, as of now, we are not appreciating Albert Einstein because his experiment is not defining what the atom is. It's just defining properties that an atom can possess. Then the other condition was, assuming the radiation's energy is less than the energy that the metal has. So if you have less energy from the radiation and the metal itself has more energy when compared to the radiation, there is no electron that's going to be knocked out from the metal and you have no transition. So with the two conditions that he gave, it now later was a base for Sir Louis de Broglie that looked at the wave and particle duality principle. And furthermore, we have Heisen's uncertainty principle that comes in to justify why it is impossible for us to have two states, that is the position and the momentum of a particle. And we have other people like, who's this? We've got people like Planck who define the energy of a photon to be a relationship between the Planck's constant and the frequency. Now, away from Albert Einstein's principle, we have Niels Bohr. Now, Niels Bohr's theories were corresponding with what these two guys had found. That is J.J. Thompson and Ernest Rutherford. That is the more reason why his definition of the atom was more acceptable, because it was in line with these two guys' discoveries. J.J. Thompson, who discovered the electron, and Ernest Rutherford that discovered the noyon, or the proton. So his definition of the atom was based on these two discoveries. So the atom that was defined by Niels Bohr was, okay, you have these energy levels, and in these energy levels, you have electrons. Now, these electrons are held in their stationary energy levels because of the force that exists between the nucleus and the adjacent electrons. So he divided the discovery that was done by J.J. Thompson in the discovery that was done by Ernest Rutherford, he brought up 3 postulates, which we're going to look at later on. He brought up 3 postulates, and these postulates define how the atom of, say, the atom of Bohr is supposed to be defined, like on in classical mechanics. So the atom that we're going to look at in classical mechanics is the atom that Niels Bohr had discovered. Now, like I always say, whatever is going to be done in classical mechanics applies to classical mechanics. Whatever is done in quantum mechanics is done in quantum mechanics. So the two are different worlds. Whatever you have in classical mechanics is going to be applied in classical mechanics. Whatever you have in classical mechanics and you put it in quantum mechanics, they are not soluble, they are insoluble because they are in 2 different phases. Whatever you have in classical mechanics cannot be done in quantum mechanics. That is the principle. Now we have the atom. Now the definition is the smallest particle of an element that can take part in a chemical reaction. We have the electron being the elementary particle that carries the current when you have electricity conducted. You have the proton that is responsible for the positive charge of the nucleus. You have the nucleus that is responsible for the definition of a mole. We did this last week. We are saying the nucleus is actually responsible for the definition of a mole because we are saying the nucleus contains 1.67 to the power negative 27 kgs. That is the mass of the proton, and that is the mass of a neutron. Now, when converted, it actually defines what 1 mole of an ion, of an atom, or of a molecule that equals to 6.2 to the power 23. That is what we are calling Avogadro's constant. Now, that is the general definition of the atom. Now we look at the most important aspect of the atom, which is the classical mechanics and the quantum mechanics. So classical mechanics is basically a form of mechanics that is used to define the movements of a given particle. In other words, mechanics is just a study that is used to define the movement of these particles. Of course, with application of the 3 main laws that govern classical mechanics. The first law, which is if you've been given a body and the body is moving in a straight line. Now, assuming that that body is not disturbed, it means it's not going to change the direction. But in this case, we have a force that is going to be applied contra its trajectory. Then that body is going to move away. It's going to move away from the point it's supposed to target. And we're calling that Isaac Newton's first law of motion. And secondly, we have this definition to say, okay, given a particle with mass and acceleration. So we are saying the force or the mass and the acceleration of this particle are proportional, which means that if they are proportional, the relationship that exists between the two should be a multiplication factor. It means the mass and acceleration are supposed to be multiplied for us to give a unit vector. And in this case, our unit vector is what we are calling the force, and that is called Isaac Newton's second law of motion. And the last state or the last law is given a particle and you are projecting it on a surface, the amount of energy that you're going to apply for you to have it hit on that surface is equals to the energy that is going to be applied when it's coming back in the opposite direction. We're calling that the reaction and action law. It's called Isaac Newton's third law of motion. So these 3 laws are the ones that govern classical mechanics. Whatever is not defined by these 3 laws is defined by classical, or is not anything that's not defined by these 3 laws is not going to be applicable in classical mechanics, but rather we're going to have it being applied in quantum mechanics. So far, is it clear?
Oui.
Okay, is it clear for everyone? Is it clear for everyone? Okay. So we're saying Niels Bohr's definition was done on an atom, and this atom's special name is called the atom of hydrogen. Now, you'd ask yourself a question, why did he do his study on the atom of hydrogen? Now, assuming I was also in the day with Niels Bohr, I would say the reason being was hydrogen is one of the easiest atoms in this world that you can use to study the nature of other atoms. Now, whatever is going to be done on an atom of hydrogen is the same principle that's going to be applied on the atom of chlorine, atom of calcium, atom of fluorine, atom of xenon, etc. It's the same thing. The principle still remains the same. So hydrogen in this case stands for maybe say a reference point for what we can actually study in future. That can be xenon, that can be argon. The principle still remains the same. A hydrogenoid is basically an atom that is a look-alike of hydrogen. A hydrogenoid is a look-alike of hydrogen. Now, this is how we're going to define a hydrogenoid. Now, we know that hydrogen only has one electron in the outermost shell. A hydrogenoid should be a look-alike of hydrogen. Therefore, given, for example, you've been given, I'll do this. Stop. Given, for example, the atom of calcium. Calcium has 40, that has 20 electron, atomic mass 40. Just a minute. Okay, so calcium has electrons, that is 20 electrons. Okay, this is visible, isn't it?
Yeah.
So calcium, we're going to define a hydrogenoid. So calcium has 40 as atomic mass and 20 electrons, 20 protons. So 20 electrons, 20 protons. We assume that you guys now understand the law of neutrality, which states that the number of protons equals the number of electrons. Of course, when there is an imbalance, you're going to have the formation of an ion that can either be positive or negative. So calcium having 20 electrons. Now, we want to form a look-alike of hydrogen. And we're saying hydrogen is any atom that has one electron in the outermost shell. Now, the look-alike of hydrogen is going to be called a hydrogenoid. Now, how is it going to be called a hydrogenoid? Its definition is going to be derived from calcium having 20 electrons. It must lose a significant number of electrons for it to have one electron in the outermost shell. Meaning, from the 20, how many electrons are we supposed to remove for us to have a unit of one in the outermost shell? We're going to lose 19 electrons. So 19 electrons are supposed to be lost by the atom of hydrogen for calcium. And at the end of the day, we're going to have a cation ion that is going to be Ca19 plus. Now, some of you might ask me a question, okay, this is going to be applicable for any atom. Of course, any atom in the periodic table. So we can have lithium with 3 electrons. That is going to be lithium. At 3. So it's the hydrogenoid is going to be like L2 plus, because we are supposed to have just one electron in the outermost shell, just one. Now, the question that one of you might ask is that, okay, Mr. DM, look, this is what you call ionization. This is what you call ionization. What is this? Ionization. Now, this ionization is actually going to respond to this question. So, assuming someone might ask this question, say, Mr. DM, okay, is it possible for you to lose 19 electrons? Okay, let me ask this question to the audience. Is it actually possible for you to lose 19 electrons?
Yes, I think it's possible, except you're going to require a large amount of energy to do so.
Voilà. So it is actually possible for you to lose as many electrons as possible. Now, the issue that comes in is what we are calling the force of attraction that exists between the nucleus and the electrons. Because we understand, to say, from our basic atomic structure, we know that the reason why we have the electron found in the orbital is because of the force that exists between the nucleus, that is the proton, and the electrons, the adjacent electrons. Now, we are saying if we want to remove an electron, we are actually working against a force. We are actually working against a force. And this force is going to require us to have more energy for us to overcome it. It's the same analogy I gave where you have an electron, not an electron. You have a radiation, that is Albert Einstein's photoelectric effect. You have a radiation that is alpha, and you have a metal. We are saying for you to knock down an electron from the metal, the energy that you're supposed to start with, that is the energy of the particle alpha, is supposed to be more than the energy that the metal possesses. If the opposite is true, you will not have an electron that is going to be ejected. It's the same principle here. If you have energy that you have, if the energy of the atom is greater than the energy you are applying to remove an electron, you will not remove any electron. But if the amount of energy that is going to be applied for you to remove an electron from the orbitals, any of these orbitals, it means the energy is going to be too much for you to actually remove an electron. So the question that might be raised is that, is it possible for you, for an atom of calcium with 20 electrons to lose 19? It is possible. But as you move towards the nucleus, the work becomes too difficult because the force of attraction that exists between the nucleus and this electron here is so strong as compared to the force that exists between the nucleus and the atom in the fourth energy level, when compared to the energy that you will require for you to remove an electron in the fourth energy level. That is how these energy levels progress. So to respond to that question, we are calling on a notion called ionization energy. And every time you have an electron that is going to be lost, of course, to the surrounding, when we talk about surrounding, we're talking about the atom's environment, So in this case, if there is energy that's going to be lost to the environment, so the energy is going to be called Planck's energy, and it is denoted by two parameters, that is Planck's constant and the frequency. So Planck's constant being equals to 6.6 times 10 to the power negative 34 joules per second. Now, we are done with hydrogen lookalikes. So now we are still on hydrogen because we have an atom of calcium, yes, we have an atom of calcium, but we are saying in classical mechanics, where we are using hydrogen as a reference, we're supposed to narrow down every atom to hydrogen. Everything is supposed to be narrowed down to hydrogen. Of course, it's calcium, but we are supposed to study the lookalike of calcium, which we are calling calcium 19 plus, which is a hydrogenoid. So whatever is going to happen to this hydrogenoid is the same thing that's going to happen to the atom of calcium. That is the principle here. So we are only scaling down the atom of calcium to hydrogenoid, that is calcium 19 plus, so that whatever is going to be applied on the atom of hydrogen is going to be the same on the atom of calcium. Because you guys, the engineering students, have learned that when the atom of hydrogen was, when the atom of hydrogen was studied with light, when the atom hydrogen when there was an interaction during this whole study of Niels Bohr, when there was an interaction of hydrogen and light, they came up with what you call spectra. So it was found that actually an atom of hydrogen has white light, and white light contains the 7 colors that are found on the rainbow. And each color, or let me say each wavelength corresponds to a color. That is physics electromagnetic spectra. Each color corresponds to a specific wavelength. Each color corresponds to a specific wavelength. So when you have a hydrogen atom, and this hydrogen atom has got red, it has got blue, it has got indigo, it has got all those colors. They are actually corresponding to the energy levels that you have. It corresponds to the first energy level, it corresponds to the second energy level, corresponds to the third energy level. And you guys are calling this series. You've got Bauma series, Lehman series, Paschen, etc. I'm sure you guys have done those things, isn't it? You've done them there?
Yeah.
Right. Now, not forgetting our subject. Our subject here is that we have the discovery of the atom, and this atom is now defined to have a proton, to have an electron, to have energy levels. Now, Niels Bohr came up with postulates. Now, these postulates here simplify everything. They simplify everything to deal with classical mechanics. So his first postulate states that you have stationary energy levels, and these stationary energy levels have electrons. These electrons are going to be found in these well-defined energy levels. These electrons are going to be found in defined energy levels. It's the same thing. It's the same thing. When you look at how houses are built, wherever you are, houses are going to be placed. Houses are going to be placed in some type of location, and you always have roads cutting across, along, etc. It's the same arrangement here. The electron is going to be found in a definite place. You'll never find a house built in the road, like on the road. Then there it calls for the council to come and demolish the house because it is not in the correct position. Now, this is what we are defining. This is what we are defining. This is what we are saying. We are saying, okay, we have three postulates, and this postulate, that is, the electron is supposed to be found in a definite energy level. Now, what happens if the electron is not found in a definite energy level? Then that calls for the third postulate. We're calling that the energy transition. Now, before the energy transition, there's one important postulate. This postulate is called the angular momentum postulate. It is defined with a formula that is n multiplied by the reduced Planck's constant is equals to n, that is the principal quantum number, over, that is going to be 2 pi. It is defined to be n, which is a principal quantum number. It can be n is equals to 1, n is equals to 2, n is equals to 3, multiplied by the reduced Planck's constant. The reduced Planck's constant is equals to, it is defined to be n multiplied by h bar. How can I write h bar? H bar should be equals to m, the mass, the velocity over the electron. So when to subscript e, and the radius. So this E stands in for electron. So H is going to stand in for not Planck's constant, but reduced Planck's constant. So reduced Planck's constant is actually equals to H is equals to H over 2 pi. 2. So H, I think you guys have seen this, but let me just show you how it's written. H bar. It's written like this. H bar is equals to H over 2 pi. So the angular momentum of the hydrogen atom is defined by this formula here. It is n, which is a principal quantum number, multiplied by h bar. H bar is equals to the mass of an electron multiplied by its velocity. Then you have this radius here. This radius is actually the radius that exists between the electron you're talking about, or the electron you're studying, assuming this is our electron, and the nucleus. So this distance is what we're calling our R. So our R actually increases depending on what your reference is. So we might have this here. We might have this inside here like that. So there are three cases. When you have the nucleus and n is equals to 1, this is the smallest thing you're seeing here. When you have R, when you have the nucleus and n is equals to 2 there. So this is our second R. Then the last one, R is equals to 3. So the simplest definition I can give for angular momentum is, you see, there's what you call centripetal. Let me say there's what you call centripetal motion before we go to acceleration and force. There's what you call centripetal motion. Now, centripetal motion is actually a classification of movement that is responsible for the movement of particles in a secular manner. This is what you're calling centripetal motion. Anything that's going to be moving in a circle is going to possess a centripetal acceleration or a centripetal force. Now, the angular momentum is a result of these two interactions. So this is how I explained, this is the simplest explanation I would give for angular momentum. You see, when an electron is moving, it has two things. It has the force and it has the acceleration. Now, angular momentum is actually the intermediate. It is the coexistence between centripetal force and centripetal acceleration. It's a thing that's in between. For you to have, this is what motivational speakers, they say, no, you're supposed to have the momentum for you to move from your problems to success, etc. They talk about momentum. The momentum is actually, I would say, it's your inner intuition, like something that you already have. So the electron has that momentum in it. Now, what's supposed to drive to push the electron into like circular orbit? There's force there. There's an acceleration that comes into play. So angular momentum is just the coexistence, or maybe it is a parameter that exists in between the force that we're calling centripetal force and the acceleration we're calling centripetal acceleration. And it is this momentum that helps us, okay, say that this electron is going to be defined in this trajectory. It is the momentum that helps us define the trajectory to say, okay, this electron is found in this circular or maybe in this orbit. It is the unit we are going to use to say, okay, for us to actually find the electron's position, we're supposed to look at these two forces, centripetal force and centripetal acceleration. Centripetal force and acceleration are responsible for the movement of the electron in this trajectory. Now, this trajectory is defined to have this special feature. Now, this special feature is what we're calling angular momentum. It helps us look at the trajectory that has been taken by the electron. The angular momentum actually gives us a vision or an insight to say, okay, the electron has taken this trajectory here. Now, why do we have a circular? Now, the question is, why do you have a circular trajectory? So we are saying we have a circular trajectory because anything in motion should possess these two criteria. The first thing is centripetal force, and the second thing is centripetal acceleration. So, angular momentum is what the electron has in itself that is going to help us say, okay, this electron, when we apply the centripetal force and the centripetal acceleration, it took this trajectory. Then the last postulate, which is the energy transition. So in his last postulate, he stated to say, assuming you have an atom. Now this atom has got definite energy levels and it has a bien definido angular momentum. Now there are two things you're supposed to consider. The atom can have what you call an emission, or you can have an absorption. Of course, in this case, we're talking about electrons. An electron can be emitted or an electron can be absorbed. Now, the definition of absorption and emission is when an electron is moving from a higher energy level, to a lower energy level. When an electron is moving from a higher energy level, for example, n is equals to 3, and it's going to n is equals to 1. Grace, what do you call that transition?
The movement of an electron from
energy
region of higher
from
to a lower energy.
Voilà.
It's emission. Oh, emission, sorry.
Emission. Why is it called emission?
Because it's being released to the outside world.
Voilà. So the reason why we are calling it emission is because at the end of the day, the energy is going to be released to the environment. This is the energy that we are calling here, E is equals to H for F, the frequency. So the transition that is from a high energy level to a lower energy level is called emission. It's called emission. And the transition that is from a lower energy level to a higher energy level, we're calling that an absorption. We're calling that an absorption. So whenever you have an emission, that is from his definition, whenever you have an emission, there's going to be energy that's going to be lost to the environment. And this energy is always supposed to be less than zero. Now, whenever you have an absorption, the system is absorbing energy. And in this case, the energy is going to be positive. The system is going to gain more energy. The system is going to gain more energy. So Niels Bohr gave a resume of the postulates that we had from Aristotle to J.J. Thompson and Rutherford. He defined those things in just 3 simple postulates. The first one was that an atom has got energy levels, and these energy levels are rods, or they are, let me say, they are houses where we are going to find our electron. The electron can be found in these definite energy levels. That was his first postulate. The second postulate talks about the momentum of a particle. A particle is going to move in a circular manner because of 2 important forces, or 2 important quantities. So 2 important physical quantities, to be specific, 2 important physical quantities. That is acceleration and force. So we're saying the reason why we have these type of trajectories because of the 2 physical quantities, acceleration and the force, the centripetal force. Now, there's something else. There's this ingredient. This ingredient is what we have ourselves. Without this one, in as much as we have the momentum, in as much as we have the force, we have the acceleration, but without this one, without this factor that is found in the electron itself, you will not have this type of trajectory. You will not have this type of trajectory. So the reason why we are saying we have a well-defined circular trajectory that is a result of angular momentum. And the angular momentum plays hand in hand with these 2 physical quantities, that is acceleration and the force, that is centripetal force. In conclusion, his atom's definition was now going to look at the principle of energy in the atom. So he says energy can be quantified in 2 types of transitions. The first one is what we are calling, calling this an absorption, which is the movement or the transition of an electron from a higher energy level to a lower energy level. Now, when you have this transition, there is always going to be energy that is going to be lost to the environment. On the other hand, absorption is the movement or the transition of an electron. Please, it's always an electron that is going to be moving. An electron is going to be moving from a high energy level to a lower energy level, from a lower energy level to a higher energy level. So if it's moving from a lower energy level and it's going to a higher energy level, that means you have an absorption, and the system is actually absorbing energy. For an emission, the system is actually releasing energy to the environment. So when you quantify these 2 energies, the energy that is going to be released from an emission should be less than 0, and the energy that is going to be quantified from an absorption should be greater than 0. Are there any questions? Any questions?
I have a question.
Oui.
So what causes the absorption and the emission? Or let me say this, what causes the movement of an electron from one energy level to the other?
Well, so the reason why you have an emission, or the reason why you have these energy transitions, is because of what happens in the environment. Now, there's what you call in another aspect of chemistry, which is called diffraction. There's what you call energy that is going to be bombarded on this atom, like the photoelectric effect. You've got this atom here. So when we bombard energy from the external environment to this atom here, you find that the atoms, or let me say the electrons, move from one point to the other. That is why from your study, or from the study that you were doing, there was an aspect you were calling energy excité, or bien état excité. So an electron can only be excited when there is an external energy coming from the environment that is being imposed on the system. So the reason why you have a transition, or the reason why electrons move from point A to point B, from the higher energy level to the lowest energy level, to the lowest energy level to the highest energy level, is because the atom itself, in its atomic state, it has been affected by a force that is from the environment. This force can be light. This force can be light. Assuming we have a metal, I'll just give an example of what happens in diffraction. You've got this metal here. You've got this metal here. So I'm sure there's someone who's done CHIMIE mineral with me. Let me see the participants. No, okay, there's no one. But so today we're looking at the structure of a crystal. So a crystal, like you guys have defined the crystal, say the crystal is a solid with faces naturally arranged, etc. Now in mineral chemistry, we define crystal to be any solid with well-defined planes, a solid with well-defined planes. Now in this case, this solid, for example, we're assuming this is an atom of copper. We're assuming this is an atom of copper. Now this is an atom of copper, meaning it has small units that are making up this copper atom. There are small units there. Now, this same copper atom is a crystal. It's falling under the class of metallic crystals. It's a crystal. Now, what happens? In diffraction, there's what you call diffraction. You've got X-ray, which most of the times the wavelength is equal to 1.5 nano, that is Armstrong's, 1.5 to the power negative 10 meters. So what happens is that we are supposed to define, or we are supposed to follow law, this is what you call law de Bragg. Now this law defines if our crystal has a well, let me say the pattern or the arrangement of the atoms in this crystal are bien defined, like they are properly defined. Like it's a crystal, you guys have said the crystal is faces naturally arranged. And these particles or these planes, they are supposed to be defined well, like bien defined. They're supposed to be bien defined. A crystal is supposed to be bien defined. Let me give an example. Let me show you an example of how the crystal is supposed to look like. So that, as we explained, you have a proper notion of these crystals. So we're going to say, okay. Voilà. So let me share the screen here so that we follow. Is it showing this one here? This, or we say crystal d'argent.
Oui.
Okay, this we use this same big one. So the reason why the atom, this is the say microscopic view of if this is how the atoms are arranged when you look at them from the eye. In the microscopic view or the microscopic scale would show this. This is how the atom looks like. This is a crystal. Now these are small units that make up the whole atom itself, make up the whole atom. Now we are saying the reason why we have those transitions is a result of, you see, these atoms here are defined by planes, and these planes are called le plan réticulier. And each plane has defined figures. You might find that this is 110, this is 221, etc. As in, for now, we are not considering all those planes. But we are supposed to understand that when you have light that is going to be projected on this atom here, you are going to have a transition that's going to take place. So if the transition is going to be in line, if it's going to agree with what we are calling loi de Bragg, then you are going to have a transition. Meaning the atom in its atomic state, when is knocked down, or when there is energy, and this energy is coming from rayon X, that is X-ray. If it's coming from X-rays, you have a transition that's going to take place. And this transition is supposed to be in line with loi de Bragg. It's supposed to be conform with loi de Bragg. Now, what happens if it's not conform with loi de Bragg? If it's not conform with loi de Bragg, this is where you have a situation where an electron is not knocked down, but the force of attraction between the nucleus and the electron decreases. The attraction between the nucleus and the electron decreases. So basically, the reason why you have transitions from a high energy level to a lower energy level is a result of the interactions from the environment. And these interactions from the environment can be, an example I have given is Rwanyo X, that is X-ray. When X-ray is projected to any atom, they have transitions. These transitions can either be emissions or they might be absorption, depending on what we are studying. Now, in a case where you have an emission, this is what we are calling the transition of an electron from a higher energy level to a lower energy level. So what happens is that the electron possesses the energy that is coming from the radiation, and at the end of the day, you are going to have the electron moving from a higher position to a lower position. So at the end of the day, we go back to our presentation. Let me just show you what happens. So what happens at the end of the day is that because the atom has possessed energy, hope it's sharing, because this atom has possessed energy from Rwanyo X, the electron now is going to move from this high energy level to a lower energy level. So this diffraction is applied in many fields of science. It is applied in pharmacy, where you've been given an example I gave today in the class of CHIMIE mineral was that you've been given a crystal, and this crystal is Panadol. Now, assuming this Panadol crystal, we are saying this is a Panadol, this is Panadol, and this Panadol is made up of crystals. That is what we are going to look at in the CHIMIE mineral. For CHIMIE organic, it's going to be something else. So we are saying this crystal here, we are doing our analysis. Now, for us to test that this crystal or this medicine actually works, we are going to apply what we are calling diffraction. Now, if we are going to get positive values, that is from the planes, I said in a crystal you've got planes, the plane reticulaire. If we are going to get a definite figure for each plane, it means that the medicine is well crystallized. Like when you were doing the crystallization, you who was responsible for the crystallization, you did a very good job. Now, if the plane reticulaire in the crystal, that is Panadol, if they are not well arranged, it means it's not going to be conform with loi de Bragg. And therefore, the values that you're going to get at the end of the diffraction are going to be different from the references that you have for the Panadol medicine. At the end of the day, the Panadol is not going to be, it's not going to be consumed by humans, because already the crystals found in the Panadol are very, 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 very important, because the structure itself of a crystal, the structure of a crystal is supposed to be well defined. When you go to organic chemistry, you have something else that defines why some of these elements appear to be in that way, and why having a structure that is different from that is going to cause issues in our bodies. So the reason why we have these transitions, like I said earlier on, is because there is energy that is coming from the environment, and this energy from the environment excites these electrons. That is why you guys were calling this état excité. It's in an excited state. So when it's an excited state, what happens? It can either move from a high energy level to a lower energy level. We're calling that an emission, or it can move from a high energy level to from a lower energy level to a higher energy level, calling that an absorption. So basically, it is the surrounding that causes these transitions. The energy from the surrounding is responsible for the transitions that you have in this atom. Is it clear?
Yes, it is clear.
Okay. So any other question from anyone? Okay. So is it clear for everyone? Is it clear for everyone? Hello. Okay. So then now a further discovery or a further study that was done on the atom, that is atom classic, is what we are going to say. We're going to define this to be Heisenberg's uncertainty principle. So Heisenberg is, would say Heisenberg, Louis de Broglie, these guys were, I would say, these guys were carrying the gospel from, they were carrying the gospel from the atomic classic, and they were carrying the gospel to mechanic classic. So these guys are like the disciples of classical and quantum mechanics. These are the people that were working in between them. So Heisenberg's uncertainty principle now talks about something that is not applicable in classical mechanics. But of course, we do not know what it is. So we're going to say, okay, it's going to be in classical mechanics because we do not know what laws govern quantum mechanics. So he says, given a particle, or this is an example that we use most of the time. So, okay, you have a plane, and the plane is moving, say, at a velocity of 20 meters per second. Now, we assume you are here inside that, or you're on the ground, and you are looking at the plane. Now, the question we're going to ask you is that, is it possible for you to find out the momentum of the plane and the position of the plane at the same time? And the response that is given is that it is impossible for you to find out the position of the plane and the momentum of the plane because it is impossible, d'après mechanical classic, that you are looking at two parameters at the same time. In other words, in classical mechanics, saving two masters at once is impossible. But in quantum mechanics, saving two masters at once is actually possible, which means Heisenberg's principle was actually a breakthrough for quantum mechanics. Because here in quantum mechanics, what you call superposition and entanglement. And these are parameters that can be done simultaneously and they have no effect whatsoever with the atom. Now, Heisenberg's uncertainty principle, it's an uncertainty principle because you cannot know the position and the momentum of a particle at the same time. That is in the world of classical mechanics. Now, this rule, when taken to the world of quantum mechanics, defines another thing. In quantum mechanics, Heisenberg's certainty principle, we call it certainty principle in quantum mechanics. Certainty principle is that you will be able to define the position and the momentum of a given particle. You will be able to define the position and the momentum of any given particle. So already you would say, or you would tell that, okay, in classical mechanics, fairly straight. In quantum mechanics, things begin not to make sense. That is the reason why Niels Bohr came up with this. He said, it is going to be, if you study quantum mechanics, and you are not astonished by how confusing it is, if you are not astonished by how confusing it is, then you have not understood it. So it shows that you not understanding quantum mechanics is actually a good thing, but it's not a good thing because you're supposed to understand what happens in the system. Now, you trying to understand what's happening in the system, at the end of the day, you trying to understand what's happening in the system will lead you into more confusion. So classical mechanics, this is where everything is straight. No, you shall do this, you shall do this, you shall do this. No, energy is found here, angular momentum, energy transition, it ends there. Now in quantum mechanics, things begin to make no sense. So some of the important formulas that we are going to be using are Planck's energy formula, which is defined as energy is equal to Planck's constant multiplied by the frequency, and the transition of any, that is an electron, either be it, what do you call this? It can either be an emission or an absorption. The energy formula is negative 13.6 over n squared, and n in this case is going to represent the nombre quantique, what we're calling a quantum number. And for a hydrogenoid, the same thing. The only difference that here we're going to have a charge that is Z, and we're going to divide by the same principal quantum number we are calling n. And the radius, like we mentioned earlier on, d'après the second postulate of Bohr, angular momentum, which is n multiplied by reduced Planck's constant is equal to the mass of the electron multiplied by its velocity, and the distance between the electron and the nucleus. We're calling that radius is defined to be n squared multiplied by 0.53 Armstrongs. So I'm sure you guys have already done some of these formulas, and they are now making some sense. Tiff?
Yeah.
Okay, yeah, so then we have the radius here of a hydrogenoid. So the hydrogen and the hydrogenoid, the only difference that is there is that for the hydrogenoid, we have the charge on all cases for the radius and for the energy. And we have what you call Rydberg-Ritz equation that is used to calculate the number of waves or the wavelength of a given transition. And it defines the 2 points, either you're moving from if you're moving from n is equals to 2 to n is equals to 3, or from n is equals to 3, n is equals to 2, you define these 2 points. This is why we have n1 and n2, the principal quantum numbers, the energy levels, then Heisenberg's uncertainty principle. So just another, let me go to this part here. Okay, yeah. So let me use this, then go to that part. So Heisenberg's uncertainty principle, which states that it is impossible for you to actually find out the 2 properties of the particle, the momentum and the position. So delta x is a position, delta p is a momentum. So momentum is defined to be the mass multiplied by the velocity. Now, it mathematically, the Heisenberg's uncertainty principle is mathematically expressed as the delta x, the delta p, should be greater or equals to h4. Now, that is Planck's constant over 4 pi. Now, if you were in classical mechanics, if the product of x and p is greater than h over 4 bar, over 4 pi, it means there is a slight possibility that you can actually capture the 2 at the same time. You are moving away from the classical world, you are moving into the quantum world. So if there is a value that's going to be greater than, because you can even evaluate what h over 4 pi is. H is 6.6 to the power negative, or times 10 to the power negative 34 joules per second, and 4 multiplied by 22 over 7 or 3.14, you're going to get a value for this. Now, whatever value you're going to get on your left, if the value is greater than h over 4 pi, it implies that you are no longer in the classical world, you are actually going into the quantum world. So in the classical world, always the value on your left is supposed to be less than the value on your right, always. Because we are saying in the classical world, it is impossible for you to know the 2 positions, that is the position and the momentum, the 2 parameters. It is impossible for you to know those things at the same time. It's impossible for you to know those things at the same time. It is very much impossible for you to know the 2 quantities, that is a physical quantity, the position and the momentum over this particle. Whenever the position and the momentum's product is greater than 4 over h over 4 pi, it implies that we are no longer in the classical world, but rather in the quantum world. So another addition to Heisenberg's uncertainty principle says that the heart of classical mechanics is Heisenberg's uncertainty principle, of course, establishes the fundamental barrier for accuracy of simultaneous measurements, momentum, and coordinates over an object. So like we are saying, it defines that you've been given 2 parameters, that is the position and the momentum, and these 2 cannot be simultaneously known, of course, in the classical world. Please note that, in the classical world. But here it says that the heart of quantum mechanics is Heisenberg's uncertainty principle, which means that it establishes a fundamental barrier of accuracy of simultaneous measurements. This is what you're supposed to underline. A fundamental barrier of simultaneous measurements. In classical mechanics, you have no simultaneous accuracy for measurements here. In classical mechanics, it's either you are here at the position or you are at the momentum. It's neither you are at the momentum and the position at the same time. It's either you know the position or you know the momentum, not 2. This is why even in the Bible they say you cannot save 2 masters at once. That is the reason why even in the Bible, if you look at it very well, everything in the Bible is straightforward. That is why we are saying it is going to follow the classical world. Whatever is in quantum mechanics is not straightforward, because you have people telling you that no, you can actually save 2 masters at once. No, it is impossible, because you will have one and you hate the other. The same principle is going to be applied here. When you have 2 parameters, that is delta x and delta p. If delta p is known, you never know the momentum of that particle. If you know delta p, which is the momentum of the particle, it is incorrect, it is wrong for you to know the position of that particle when you are in the world of classical mechanics. But of course, when you go into the world of quantum mechanics, things begin to make more and more sense. So now we are now going to the world of classical quantum mechanics. Now we're supposed to look at, because the whole module itself, CHIMIE atomistic, is all about these histories and principles, but they begin to make sense at the end of the day, because they are all build-ups from one to the other. Now, the transition, or maybe let me say the prophecy from Sir Albert Einstein on the photoelectric effect was appreciated by a famous scientist by the name of Lewis de Broglie. Now, before he actually gave the appreciation, there were two, maybe let me say the young brothers carried out an experiment, and this experiment is called the double slit experiment. So in this experiment, it was because, okay, this is how it was done. Albert Einstein did the experiment in 1915, somewhere there. He did the experiment, the photoelectric effect. Later on, there was nothing to do with it. Like, he just ended there because no one was agreeing with what he did. Now, you have the double slit experiment, and you've got Lewis de Broglie. So Lewis de Broglie comes in with a principle of the duality principle, and the double slit experiment is just a justification of the duality principle. So in other words, it's Albert Einstein who gives the photoelectric effect. Then in future, Lewis de Broglie gives a justification, or he gives meaning to Albert Einstein's work. Then you see him, he just gave a postulate. He just said, okay, if you've got this, you've got this, you've got this, and you've got this formula. Now, with the double slit experiment, it just gives us more information as to how we are relating to the formula, which is h over the momentum. So h, of course, is Planck's constant, and the momentum is the mass multiplied by the velocity. So we'll start with the double slit experiment, so that at least when we go to the Broglie's principle, things begin to make more sense. So the Broglie's principle is just a prophecy that was done some time back by Sir Albert Einstein, where you have a radiation that is going to be a radiation, and you have a metal, you've got electrons knocked down, and those things. Now, because those days, let me say, that time, Albert Einstein didn't understand what he was doing. He was just doing it because everyone was looking for the definition of what an atom is, what is the makeup of an atom, etc. Now, in future, someone came to appreciate his work. He said, okay, if this atom of copper, we're assuming that's the plate we're using. If this atom of copper has small, tiny particles, and these small, tiny particles, we're calling them the atoms. We're calling them small atoms. As in, it's an atom of copper, because this copper atom is made up of small atoms that make up this atom. It's like the way we are. We are small. We are atoms of. Then our atoms are a result of tissues, cells, and all those things. And you get to have an organ, etc. That is the biology behind the cell, tissue, and organ. Those are small atoms that make you the bigger atom. What? So we have this atom of copper here, and you've got a radiation that can be alpha or beta, depending on what properties you are looking at. So if the energy, like we said, if the energy of this alpha particle is greater than the energy of the metal here, what is going to happen is that you're going to have an electron that's going to be ejected. An electron that is going to be ejected. And this electron is going to have an energy we're calling HF. And this energy is what we are defining to be a photon. So this is a photon, actually. Now, one fascinating thing is that the question that Lewis de Broglie, or maybe let me say Albert Einstein, didn't ask himself was that, what's happening here? You have a wave, and you have a metal here. Then you have another wave here. What's happening here? So Lewis de Broglie and the young brothers brought everything together. They were saying, okay, if I start with a wave here, and I project the wave to this metal or this atom that I have of copper here, and I'm producing another wave, then there must be something fishy here. It must be that this so-called atom has got two, or maybe it has got something inside it that we do not really understand. Now, it is called the wave particle duality principle, because we are starting with a wave, isn't it? We are starting with a wave here. We say this wave might have, or mostly has, 1.54 Armstrongs as the wavelength. That's the wavelength of this alpha particle. That is the wavelength of this alpha particle, 1.5 Armstrongs. Now, we're starting with the wave, that is the wavelength. And you hit this metal here. Normalement, what is supposed to, from normal thinking, we might assume, okay, no, the wave might be reflected, it might be refracted, all those things. Huh? Then you have another electron, or you have another unit of energy that's going to be produced. Now, if you look at what's showing here, is that from my other presentation is that you have Tuma waves showing that a photon is being ejected. Okay. So now, with that being mentioned, you now begin to ask yourself questions. I started with a wave and I am getting a particle. I started with a wave and I am getting a particle. Okay, it doesn't make sense. So you've got the Young brothers here. So the Young brothers experiment is called the double slit experiment, meaning you have a particle with parameter here is X, Y, and Z. Of course, in quantum mechanics, so they're defined to be parameters, or that is X, Y, Z defines the principal quantum number, the angular quantum number, the magnetic quantum number. So you have got a particle here, and this particle is producing what we are calling our alpha radiations. Now, we are projecting this alpha radiation into these slits, as in here, we are starting, this is just a representation, like an analogy of how you're supposed to understand this. Like if this is a double slit experiment, you've got a slit there, another slit here. What it is that you're not starting with two rays, no. This is just for understanding here, no. Normally it's just one, you're starting with one. This is the double slit experiment. You're starting with one. This is a particle that is going to produce alpha radiation, It's going to go like that. Now, one fascinating thing is that when it reaches the two slits, it divides. One goes in that, another one goes there. One passes through this slit, and the other one goes through that slit. And at the end of the experiment, it joins back and it forms a dot on the plate. This is the detector here. It forms a dot. So when the experiment was done several times, let me say it was done maybe at an effective of 20, you find that at the end of the day, there were a lot of these small, tiny dots that were observed here. Now, when the plate, that is this plate, the detector plate, was taken for further analysis, it was found that these dots actually represent what we are calling wave interference. Wave interference, because every time the wave was going through this slit, it was a normal wave, of course, with a normal wave like that, normal trough and crest. When it came here, there was an interference that was coming here, because it's one, as in you guys have done physics and you understand the principle of interference and what do you call this? There's interference, destructive and constructive. Now here, our interference is constructive because we have new crests and new troughs, etc. So the thing is, you're starting with one particle here, and this particle is producing two different, what do you call this? It's producing two different, it's going in two different directions, as in you've got this here and you've got that there. So now, the question is, now, how is it possible for me to have these dots at the end of the day? So the reason is as a result of what happens here before you even get to the slits themselves. So there is a factor of what is it called? It's called diffraction. Diffraction, if I'm not mistaken. In physics, there's an aspect of diffraction, that is when a wave is I think when there's interference of the wave, there's diffraction. I'm sure there's diffraction. Then there's what you call constructive and destructive interference. So the diffraction here leads to the formation of two separate, let's say you've got this wave going in that direction and this wave going in the other direction. Then at the end of the day, because they are from the same family, they're from the same particle, they were produced by the same particle. Just after this slit, you have the wave forming, or there is what you call constructive interference that is going to take place. And this constructive interference is the bonding, or maybe when we say when the coming together of these two particles that were projected in these two slits, then you have constructive interference and the particle is registered here on this plate. So now, when this was done several times, of course, with these two aspects of diffraction, interference, where we have constructive interference that's taking place at the end here, it was recorded that you have this type of, or let me say, this type of representation on a detector plate. Now this raised question, say, okay, I'm starting with a particle here, I'm starting with a particle, but how come at the end of the day, I am registering wave patterns? Why am I registering wave patterns? It doesn't make sense. I am starting with a particle here, like we said. We are starting with a particle here. This particle is being called alpha. It has a wavelength of 1.5 angstroms. And it's being hit. This is Albert Einstein's photoelectric effect. This particle is projected on this metal, this atom. At the end of the day, you have this wave that is produced, this energy that is produced here. This energy we're calling a photon, that is quantified by the formula Planck's constant multiplied by the frequency. You have a wave and you have a particle at the end of the day. It doesn't make sense. So now that led to the notion or the postulate we are calling the wave-particle duality. So it is not wrong for you to define an atom to be a particle or a wave. An atom can actually be a particle or it can be a wave. Now, this definition is correct because we are now going into the world of classical or quantum mechanics. Because in the world of quantum mechanics, we allow such possibilities, that is superposition. In the world of classical mechanics, it is wrong for us to say that an atom is actually a wave and a particle. It is actually wrong for us to say that this is a wave and a particle. So this is what we are calling the double slit experiment, because you have two slits and you've got one unique particle. At the end of the experiment, you find that, or maybe let me say, during the experiment, the particle divides and goes through these two slits that you have here and constructs, that is constructive interference, and unifies to form one more particle. And this particle is registered on the plate. Now, with further analysis, you find that on this plate, you have wave patterns. And these wave patterns, like they bring another notion. And this notion is going to be like, okay, if this is a particle, how come I have got waves at the end of the day? So it just shows, or it's evidence to show that actually an atom is a wave, an atom is a particle. So it can actually exist in two forms. That is the more reason why I would, okay, personally, I would also say, from my own point of view, I would say the definition is correct, because how would you have a transition that is from a higher energy level to a lower energy level? You have this transition. Now the question would be, why is it that the energy that is going to be produced here, the energy that you're going to produce here, why is it going to be quantified as a wave? Why is it going to be quantified as a wave? Like at the end of the day, you have an atom and you are removing, or you have a transition that is from a higher energy level to a lower energy level. Normally, what is supposed to happen from our own kind of thinking is that when you're moving from this to this one should just drop out, as in it just drops out. But the dropping out of this calls for an energy transition called emission. And this energy is what we are classifying to be the Planck's constant multiplied by the frequency. Now, this energy here is in what form? It's in the form of a wave. It's in the form of a wave. So I would also say the atom is actually both particle and a wave. It is correct to say that the atom is a particle and a wave. Any questions so far?
Okay, I have a question.
Oui.
Okay, since an atom is both or can exist, okay, let me say this. Since an atom is both a wave and a particle, and of course we know that one of the properties of light is that light can exist as a particle and also a wave. So is there any relationship between an atom and light?
Oh, voila, there is actually voila. That is a very, very good question. Now, this question now leads us to what I mentioned earlier on here in the atom of hydrogen. So hydrogen, like I said, you guys have done the spectrum of hydrogen. When hydrogen interacts with the environment, it forms a spectrum. And these spectrums are what you guys, Mr. Daniel, you guys in the engineering class have done the spectrum, the hydrogen. There's Paschen, there is Lehmann, there is Baumer, there are all those series. And each of those series defines a specific color. Now, color, in physics, color can be, personally, I can define color to be a wavelength, because there is another aspect of chemistry that deals with wavelength of chemicals, and what we're actually looking there, what we're actually looking at there is the color, but the aspect or the principle behind the colors is the wavelength. So it is correct for you to say that an atom is actually light. It is made up of, okay, it wouldn't be correct to say it's light, because light is also a particle. So light is going to fall in the particle definition. It would be correct to say actually a particle has, okay, as in the particle, that's the particle itself, because light is a particle. Light is a particle. We would say, okay, the atom is a particle and it is a wave. Light is also a particle and it is a wave. An atom can possess these characteristics. Now, it is true. It is very true that we can have an atom being defined to be light. That's not wrong. Personally, that is correct, because when you look at an aspect of analysis called spectroscopy, you've got chemicals. The reason why you've got chemicals, okay, this is a question I've always asked myself, and I finally found the solution. The question is, why is it that water is colorless? The question is, why is that water is colorless? The reason is, it's because the particles or the atoms found in water have a lesser wavelength as compared to the wavelength that is defined in the ultraviolet. So ultraviolet is defined from, let me say, 200 nanometers to 400 nanometers. That is the definition of the UV spectrum. So anything outside this spectrum is going to be defined neutral, as in doesn't have a color. So water is found outside. Water I think water has a wavelength of 190 something. It doesn't like jump in it's not found in the domain that is 200 to 400. This is the reason why it's colorless. And of course, there are other reasons why it's colorless, but the spectroscopy side is that it's colorless because the wavelength of water, or the wavelength of the atoms, because the atoms, those atoms that you are talking about are actually particles, and they possess both particle nature, and they possess both the particle and the wave nature. So it brings us back to the definition of light. So because of that notion, where the water molecule has a lesser wavelength as compared to the domain, that is 200 to 400 nanometers, water is not found in that domain. And this is for this reason why you've got water that's colorless. The same reason, copper 2 sulfate. Copper 2 sulfate is blue because it is found in the visible, there's what you call visible domain, and what you call the ultraviolet domain. So the visible domain, this is where you've got small wavelengths from 200 to 400 nanometers. Now for visible domain, it starts from 400 to 600 or 800 nanometers. It depends with the scale that you're using. So the reason why in other words, to just give you guys another insight, the reason why some chemicals appear to be blue, the reason why some chemicals appear to be red is because they are actually absorbing a specific type of light or a specific type of wavelength. So it is actually correct for you to say that light is a wavelength. It's correct. Light is a wavelength, or blue, the color blue is a wavelength. It's correct, because these lights or these colors, blue, red, etc., those are wavelengths, and they are defined in the spectrum, the spectroscopic spectrum. So yeah, it is correct for you to say that an atom is actually light. Yeah, it is actually light. There's no problem there. There's no problem. So if you want to actually understand more about about the colors and all those things. It's another field in chemistry called spectroscopy. You look at chemicals, their structure, and how they interact with light. You look at the structure and how they interact with light, and each chemical has got a type of orientation when, for example, copper-2 sulfate. When copper-2 sulfate is projected with blue light, of course, it's going to absorb the complementary color. If copper-2 sulfate is projected with red light, it's not going to absorb that color, and you won't have the result at the end of the day. So those are the things that you look at in spectroscopy. So any other question other than that? It's correct for you to say it's correct from what we've actually put out from our discussion. It's correct. I would say it's correct for you to say an atom is actually a particle and it's a wave, and you can further classify it to be light. C'est bien. Any question?
C'est bien.
Any other question? Grace. Grace. Mentioned. It's an MD.
No question.
No question.
Okay, so we conclude with quantum mechanics. So quantum mechanics is the most interesting part of atomic structure. So the classical mechanics is this part that defines the whole definition of a normal atom. But in quantum mechanics, you have all these bizarre reactions, all these bizarre rules, and all those things that are happening that are not just like natural. It is for this reason when Niels Bohr mentioned to say, if you are not astonished by how bizarre the quantum world is, then you have not understood it. But like I said earlier on, it is our duty to understand the quantum world because we want to find out why is it that the quantum world behaves in that way. Why is it that the quantum world behaves in that way? So in classical mechanics, we define an atom to have three elementary particles: the electron, the proton, and the neutron. In quantum mechanics, we define the atom to have elementary particles and the sub-elementary particles. So the elementary particles, these are what we are calling the proton, the electron, and the neutron. Now, the sub-elementary particles that are found in the nucleus that are responsible for the interactions between the proton and the neutron are what we're calling quarks. Now, we've got what you call there are 16 types of elementary particles, but for the sake of this study, I always restrict myself to the 6 that are found in the nucleus, because there is always going to be this question. One of you is going to ask me this question: okay, if we have another set of 6 types of electrons, or maybe 6 particles that are found in the electron, one of you would ask this question, and it's a very good question. Which amongst these particles is responsible for chemical reaction? Which amongst these particles is actually responsible for chemical bonding? Okay, that is a chemical reaction still. Which of these is responsible for the transfer of electrons, etc. That is the reason why I always restrict myself to the particles that are found inside the nucleus and not in the electron. So you've got 6 quarks that are found in the nucleus, and you've got the strange, the up and the down, the charm, and you've got up and down, you've got the bottom and the top, you've got the charm and the strange. These are the quarks that are found in the nucleus. They are responsible for the attraction, that is the proton and the neutron. You know that the proton is positive and the neutron is 0. So the attraction between the two, like 0 and plus, the attraction that exists between the two is a result of these quarks. So now, Erwin Schrödinger is the father of classical quantum mechanics. So he's known for this famous experiment called the cat experiment. Now, the cat experiment is used as reference for us to understand what it actually means to be in the world of quantum mechanics. It is actually a reference for us to understand what happens in the world of quantum mechanics. So his experiment was done on a cat. Now we can also do this experiment on human beings, there's no problem. So his experiment is called a thought experiment. So it actually brings out another notion. This notion is that quantum mechanics is actually something that happens in the mind, because everything in the mind is possible. It is actually possible for you to be in 2 places at the same time. It's actually possible for you to be a president in your head. It's possible. It's called a thought experiment because it was actually thought, and it was practically done some time later, as in to just solidify the thought experiment. So this is what the experiment was all about. You've been given this cat, and you have a radioactive source. So you place the cat in a box, and you also put the radioactive source in the box. Now, assuming you are just a normal person that does not understand classical mechanics ni quantum mechanics, they ask you a question. We have a cat in this box, and we've put in radium, and the half-life of radium is going to be in the next 2 minutes. What is going to happen to the cat? Is the cat going to die? Is the cat going to live? What is going to happen to the cat? The normal response that anyone would give is that the cat is going to die. Now, that response is correct selon classical mechanics. It is correct. Normally, when you have a cat exposed to radioactive sources, it's supposed to die. It ends there. Now, in quantum mechanics, because we have aspects of uncertainty, this is why Heisenberg's principle is valid in this world. Because we've got aspects of uncertainty, it's actually wrong for you to say the cat is dead. It is wrong for you to say the cat is dead in the world of quantum mechanics. Now, there's always this aspect that I always think about. I have never really gone deep in researching about this. What happens to maybe say radium when it expires? Is there any effect when a radioactive substance expires? Is there any effect whatsoever? It's a question for everyone. Is there any effect when a radioactive substance expires? Okay, maybe this question can be changed. What happens to poison when it expires? What happens to poison when it expires? Does it lose its poison power? What happens to poison when it expires? As in, this is a question that everyone might answer. What happens to poison when it expires?
Okay, in some sense, I think it becomes more poisonous.
It becomes more poisonous.
Still remains poison.
Well, it still remains poison. Poison is poison. There's nothing like, no, it becomes more poisonous. Poison is poison. So it's the same principle here. In as much as the radioactive source was like it expired, it's still normalement with our knowledge from classical mechanics would say the cat is dead, because we know the effect of radioactive substances on these living things. Now, in classical mechanics, that is correct. In quantum mechanics, it's strong, because in quantum mechanics, the notion that is being brought out here is the notion of you are thinking, and you know that these things can actually happen at the same time. Now, if these things can happen at the same time, it brings us to another aspect of quantum mechanics we are going to be calling entanglement and superposition. So we're going to use this as explanation for the cat experiment. So in the cat experiment, you have this cat, and that you've got this box, you've put the cat there, and you've got the radiation. At the end of the day, after 24 hours, the correct resolution is supposed to be the cat is dead. There's nothing like it's alive, it's dead. Now you find that the cat is alive. Then you'll be like, what happened? So it might now here's what happened. You, as the physicist or the chemist, was doing this experiment, and I came in as a thief, and I actually stole the radioactive source. When you just put it there, as the thief, I thought it was something valuable, and I stole it. And you were thinking that the cat is going to die. On the other hand, the cat is still alive because the radioactive source is not there. Voila. So it is wrong for you to say it is dead, because in quantum mechanics, we believe that the cat is in a state of superposition. It is both dead and alive. Now, if it is both dead and alive, now what possible resolution can we actually go for? The possible resolution we can go for here is observation. So quantum mechanics is just a type of mechanics that deals with particle observation. That is the simplest definition I can give for quantum mechanics. Quantum mechanics is just this type of mechanics that looks into detail, say, okay, you've been given this type of arrangement what is going to happen? Your resolution shouldn't be a resolution coming from correct, like let me say possible answers, like what is your name, Dalitso Mwanza? No, should be no, my name is Dalitso Mwanza, a student at the Shanshan. So those solutions should be something that is going to come from an observation. Now, from an observation, it does not mean that when you're carrying out a titration, you're going to have a blue precipitate at the end of the reaction. No, you might be given a complexometric titration, you as student A, and student B might be given a gravimetric titration. And if you assume you're going to get the two results at the end of the day, then you are going to both get wrong values. But this experiment, the titration that is complexometric and gravimetric, are going to be based on observation. Your results are going to be based on observation. It's the same here. Quantum mechanics results are based on observation and nothing else. So the cat is neither dead nor alive. It is dead when you find out that it is actually dead. It is alive when you find out that it is alive. When you go and check in the box, okay, the radioactive source wasn't active, or maybe the radioactive source wasn't there. The radioactive source was stolen. The cat is still alive. You made the observation, you find that the radioactive source isn't there and the cat is still alive. No, the cat is dead. You made the observation, you found that the cat was dead. That is what quantum mechanics bases its argument on, its observation. Now that brings us to a notion we're calling superposition and entanglement. So superposition is this behavior that the atom or the electron possesses. So you find that an electron exists in two places at the same time. That is why I like the definition that has been given here. It says that Heisenberg's Centripetal Principle is one thing that cuts out the barrier of simultaneous accurate measures here. It says the heart of quantum mechanics is Heisenberg's Centripetal Principle that establishes a fundamental barrier for accuracy of simultaneous measurement of momentum and coordinates of a quantum object, which is true. Because in quantum mechanics, we are going to be looking at two aspects at the same time. Entanglement and superposition, these go hand in hand. Superposition is the ability of a particle to exist in two places at the same time. Assuming you've got a Dalitso Mwanza here in Morocco and a Dalitso Mwanza in Zambia. Now, superposition is that whatever effect is going to be done on Dalitso Mwanza in Morocco is going to happen to Dalitso Mwanza in no, that is entanglement. Sorry. Whatever is happening, whatever I can actually be in two places at the same time. That is superposition. Dalitso Mwanza here in Morocco. Dalitso Mwanza can be in Morocco. Dalitso Mwanza can be in Zambia. Dalitso Mwanza can be in what do you call this? Dalitso Mwanza can be in South Africa at the same time. We are calling that superposition. Now we will know the position that Dalitso Mwanza is taking only if C is almost C, if we know where he is, and this can only be done by observation. We can only know where I am by observation. That's all. We can only know where I am by observation. Now, entanglement is the characteristic effect that is done on a particle that is in a state of superposition. Entanglement is a characteristic of a particle that is in a superposition. Now, what does it mean? It means assuming that you've got Dalitso Mwanza in Zambia and Dalitso Mwanza in Morocco. Now, these particles are of the same nature. They are both Dalitsos and they are both Mwanzas. Now, whatever is going to be done to particle that is in Lusaka, Zambia, is going to affect directly the particle that is found in Morocco. So it's called the spooky action at a distance. That is, whatever interaction that is going to happen to the particle in Zambia is definitely going to happen to the particle here in Morocco. So quantum mechanics calls for two important principles: superposition, the ability of a particle to be found in different places at the same time, which is impossible because we were saying in classical mechanics that it is impossible for you to know the momentum and the position of a particle. It is impossible, but it's actually possible for you to know the momentum and the position of a particle in quantum mechanics, because that calls for the notion, the superposition. Then there's another notion we are calling entanglement, the ability of a particle given point A and point B to interact at a distance. We're calling that interaction the spooky action at a distance. So whatever is going to happen to particle A in point X is going to happen to point B in point at point Y. That is what we are calling entanglement. And it is for this reason why the classical model is going to be considered wrong. If you notice what I put here, this classical model is going to be considered wrong in quantum mechanics, because in quantum mechanics would be all these three postulates. These three postulates are invalid in this world. So if you look at, this is one thing I want you to look at, this here and this here. In quantum mechanics, the electron is found everywhere until you carry out an observation. So it is wrong in one sense to say that the electron is actually found in n is equals to 2. No, it is very wrong for us to say the electron is found in n is equals to, just like this here. Let me show you. This here. It is in classical mechanics, it's correct to say that the electron is found in n is equals to 3, n is equals to 2, n is equals to 1. It's correct in classical mechanics. In quantum mechanics, it's wrong for you to say the electron is found in n is equals to 1, n is equals to 2. It's wrong because we are looking at two important aspects. We are saying the electron can actually be found at point A, at point B, at point C, at point D at the same time. So what is going to differentiate, or what is going to help us know its position or where it is actually found is by observation. So quantum mechanics just calls for accurate observation and you have your solutions resolved. Now, with that being mentioned, we are going to have a small resume of what happened, like everything that we did. This is the reason why, personally, when I start doing this course with everyone, I start with the atom's definition from way back. It's not important, but it is important because it is going to give you a view, a picture of what really is the atom in these two worlds, the classical world and the quantum world. So you look at the definition of John Dalton, it's just a normal ball. It is indivisible, it ends here. There's nothing that you can divide any further. You look at J.J. Thompson's discovery, here you just have electrons. You just have electrons. And of course, like I said, whenever you have positive, it's correct to say that there's something negative. It's correct. But you have to do your analysis for you to find out the positive that is there. Then we have J.J. Rutherford, or Ernest Rutherford, who came up with a model of, let's say, you've got a fly at the center of the cathedral, and the cathedral terraces, this is where you find the electrons, which is just maybe a lookalike of what Bohr came up with. Niels Bohr's is just a derivative from these two guys, J.J. Thompson and Ernest Rutherford. So Niels Bohr's atom or model is like this, with the three postulates. Now, an electron found in stationary energy levels, angular momentum n is equals n multiplied by reduced Planck's constant is equals to the mass multiplied by the velocity multiplied by the radius that separates the two distances. Voila. And the last one, that is the energy transition, absorption, and the emission. The energy, when an electron is moving from a high energy level to a lower energy level, we're calling that an emission. When an electron is moving from a lower energy level to a higher energy level, we're calling that an absorption. And the absorption is the energy that is going to be gained by the system, and the emission is the energy that's going to be released to the surrounding or the system itself. So now, one important aspect you're supposed to notice is the way the atom is drawn here is different from the way the atom is drawn here. So here, it calls for the principle of uncertainty, which states that you can actually know the position and the momentum of these particles. We are calling this the principle is called Heisenberg's uncertainty principle in all the books, It's called uncertainty principle. But I would like to call it, in quantum mechanics, I would like to call it Heisenberg's certainty principle, because we are certain that it is actually possible for us to find the position and the momentum of these particles. So this is the reason why it is actually drawn something like, okay, this model here would help us define how the classical quantum model is, but I would rather use this one here. This one shows that you do not have orbitals that are around like that, around the nucleus, no? You just have spots. We are calling these spots electron clouds. And in these electron clouds, this is where you find the electron. Now, the electron is only found when you observe. You don't just say the electron. Here we're saying, here you will say the electron is found in n is equals to 1, in n is equals to 2, in n is equals to 3. you've got one electron. In n is equals to 2, you have one electron. In n is equals to 1, you have one electron. In quantum mechanics, it will be impossible for you to tell that the electron is actually in n is equals to 1, in n is equals to 2. The electron is found per 2. The only thing that is going to remain is you carrying out the observation. Is it found in n is equals to 1? Oui. Is it found in n is equals to 2? No. It's found in n is equals to 5? Oui. Is it found in n is equals to 6? No. It's found in n is equals to 7? No. So it's all about observation. So quantum mechanics only calls for observation. This is the evolution of the atom. And this is where we are right now. We are in the quantum mechanical model. We are still discovering more particles that are found in the atom. So like I mentioned, in quantum mechanics, you've got sub-elementary particles. In classical mechanics, you've got elementary particles, the proton, the electron, the neutron. In quantum mechanics, you've got the elementary particles, of course, the proton, electron, neutron, and you've got sub-elementary particles that are found in the proton, that are found in the neutron, that are found in the electron. Yeah. Then it now takes us to quantum numbers. So quantum numbers, when you look at this, quantum numbers can be used in, okay, another application of quantum mechanics is quantum computers. Quantum mechanics is used to build up these computers. The fastest computers on this earth are actually quantum computers. This is why you have 1 and 0. So the quantum world understands these two values. You've got 1 and 0. You've got ones and zeros. That is the quantum world. That is the language that computers understand. So we've got 4 types of quantum numbers. That is the principal quantum number, azimuthal, magnetic, and spin quantum number. The principal quantum number just designates the energy levels of any given atom. The azimuthal gives us the definition of the shape of how the let me say the shape and the size. Shape and orientation of the orbital. This is going to be done on the X, Y, and Z plane. Then you have the magnetic quantum number, which is the range from the angular quantum number. So azimuthal is called angular quantam number or secondary quantum number, as the name shows. So magnetic quantum number is a domain, or it's a range from the negative quantum number, the angular quantum number you have here. Assuming you have -2, we can even do an example here so that we understand what we are talking about. So that we understand. So I'm sure and certain that you guys have that quantum number. So we're just going to pick one, the p orbital. So the p orbital has a, so we do this. Set table. So we are going to say orbital. So in this case, we are looking at the p orbital. So we have n can be any integer except 0. So it's n at 1, 2, 3, 2, 3, 4, etc. Then you've got the azimuthal L. For the p orbital, it is defined to be -1, 0, and 1. So these are orientations of the X or Y plane. So -1 stands for what you guys have been seeing, or you have seen as px. This is what you call px.
It's 9 o'clock.
That is what we are going to call this here. There's py. This is the 0 you're seeing here. These are the orientation. This is why I'm saying the orientations in space for these orbitals, then the pz. And this px, py, pz is very important because it comes in the aspect of hybridization. So you've got magnetic ml, which is just a range. No. which is just the range. That is no, this is what this is a mistake I've made. So this is supposed to be here, the range, and here we're going to have 1. And ms is the spin, that is positive 1/2, positive 0.5 up, and spin down, negative 0.5, like that. So yeah, so these are the types of like these are the quantum numbers. So we've got principal quantum number that can be defined from 1 to infinity, except 0. Then angular quantum number. So angular quantum number of each shell is well defined. So if we are looking at Kush S, the angular quantum number is 0. So we can even add, say, layout. So Kush S, Kush D, Kush F. So Kush D is a build-up from P. You're going to have 1, 2, and Kush F, you're going to have 3. So these are the angular quantum numbers. So L is equals to, or maybe let's draw a proper table. A proper table we're going to have. So we have a P here, and we have 1 there. So L for the P orbital is equals to 0 for the S, sorry, is equals to 0 for the D, for the P is equals to 1, for the F is equals to 3. Then the magnetic is just the range. That is from the negative value to the positive value. So the magnetic is going to be the range from 0. There's nothing like from positive 0 to negative 0, so it's 0. There is no magnetic quantum number for the S orbital. For the P orbital, it's going to be negative 1 less than or equals to, so less than or equals to ms or ml, sorry, less than or equals to 1. So the value in between there is 0. Same thing applied here. You have negative 2 less or equals to m, l less or equals to, I don't have the less or equals to here for simple, because I'm supposed to go to the equations and look for it. But yeah, it's less or equals to negative 2 less or equals to positive 2. And the last one here is negative 3 less or equals to ml less or equals to positive 3. So less or equals to, please note that it's less or equals to, 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 less or equals to. So these are the things that actually govern quantum mechanics, the quantum numbers. The quantum numbers. There is, well, there is, these numbers just look as if they're just 1s and 2s and 3s, but they actually define where the electron is found. They actually define where the electron is found. So in another aspect of this study, we can actually look at the probability density. That is the probability density for us to find an electron. Then there, we're going to call upon another notion of statistics called distribution normal. So normal distributions can also be used in quantum mechanics. So quantum mechanics, in other words, it's just, it's the atom, of course. Now you are putting in other principles because we are looking for our question here is, where is the electron? Where is the particle? That is the question here. So it calls for probability, because you'll be like, okay, what is the probability that we're going to find the electron in point X? What is the probability we're going to find the electron in point Y? So it calls for that type of probability, and the probability is going to be governed by what we are calling the normal distribution. Then you know that the atomic structure, or maybe say the atom itself, is simplified by what we call the periodic table. And the periodic table is divided into classes or blocks. So we've got the S block, the P block, the D block, and the F block. Then each block represents the number of, or maybe it designates how many, let me not say block. Each period designates the number of energy levels you have. It also shows us the interaction between these blocks. Some have S and P blocks, some have S, P, and D blocks, some have S, P, D, and F blocks. So the periodic table sums up everything. This is the S, the P, and the F block. It shows us the properties, the physical properties of these elements, the chemical properties of these elements. It tells us information about the number of electrons you find, the number of protons you find, the neutron number, the mass number, and another aspect is the symbol, which we are calling the nuclide notation. Then, with respect to the quantum numbers, there are rules that are supposed to apply when you're looking at the electron configuration. So electron configuration here, it's the building up principle, which is called direct deconstruction. Then there's Pauli's principle and Hansa principle. So Pauli's principle basically is the remplaçage, where you are always going to start with the energy level that is lowest and go to the energy level that is highest. Now, you're not forgetting that the energy level that is lowest is supposed to occupy the total number of electrons before going to the highest, to the next energy level. It's just an addition to regular construction. Regular construction is 1s, 2s, 2p, etc. Now, reg de Hand, this one says, or it states that whenever you are carrying out remplaçage, the construction, you are not supposed to forget that if there is an uneven distribution in the number of electrons, what you're supposed to do is share the electrons between the electrons in the same energy level. His principle is that if you've got electrons, if you've got this type of orientation, you have up, because the rule is you go up, and you come down like that. You come down like that. Now, assuming that it was something like this, and you only had 3 electrons, normalement, you were supposed to draw, okay, let me say, you had, how can I put this? His rule is, normalement it's up, down, down. But if you have only 3 electrons, instead of you saying up, down, you say up, like that. So his rule calls for a balance. It calls for having a balance in the distribution of electrons, because the rule that is the regular construction is when you have cars can tick, you go up and down, you go up and down, you go up and down, etc. But now regular de Hand states that if you are in the same energy level, if the energy level is P, if this was our P, if this was our energy level P, and you have 3 electrons, it is incorrect for us to say that, okay, we're going to have this type of arrangement. We have 1 electron there down, then you have another one here. It is wrong, because this energy level is not balanced. So it's calling us to apply reg de Hand, which states that the electron is supposed to be balanced in a given energy level for as long as the quantum number is the same. The quantum number, no, this is not 1. The quantum number here might be 2, it might be 3, it might be 4, it might be anything. Yeah, so the principal quantum number can be any other value. So these are the rules that are going to be used to now sum up whatever we've done from the first electrons. We have Pauli's principle, the comma remplaçage, Hans principle, and now we go to the periodic table. The periodic table, which is a table of classification, it gives us a resume of everything. It gives us a resume of everything. The periodic table is divided into blocks. The periodic table is divided into groups. And we have periods. The periods designate the number of energy levels you have in an atom. The groups represent the number of atoms or the number of electrons that you're going to gain, the number of electrons that you're going to lose. Yeah, and simply, yeah, it's a table of classification. You use this table to classify what atom is what. Why is it a metal? Is it a non-metal? Is it a transition metal? Is it coming from the lanthanide and anthanide series, etc. Otherwise, that was everything to do with the atom. Otherwise, thank you very much. And I think this marks the end of our class. Yeah. This marks the end of our class. So if you guys have questions, you can still ask the questions, but I'm done with my presentation. Any other questions? Any other questions? Because I'm done with the presentation.
Everything is clear for me. There are no questions.
Okay, there are no questions. The advantage that Grace is doing this class for the third time. Munchindo.
No.
So I've got a question. I'm going to give you guys an assignment, which is due tomorrow. Are we d'accord?
No questions.
Are we d'accord?